Yeah, so I think we can start now. Some people will be joining later on. I think it's always like that, but we will start now. It's 6 p.m. Central European Time. Hello, everyone, and thanks for joining. Today we have a very interesting topic. We have a CFD analysis of nanofluids, fundamentals, applications, and ANSYS Fluent demonstrations. And I would like to begin with the sort of rules for today. So if you are not speaking, you please may turn off your camera and mute your mic. You can also write your question in the chat. We have a live chat during the webinar. And you can go ahead and complete the survey. We have prepared a poll, questionnaire, let's say, to understand your background a little bit better, to shape the webinar into one or another direction based on your feedbacks. So please go ahead and check the survey in the chat. I would like to start with the brief introduction about Wired White and explain a little bit what we do and why we do it. So basically, we have created and launched an engineering platform, an engineering community, and we have basically two major user types, which we call customers and partners. So basically, a customer, it can be an individual, it can be a student, it can be a young professional, a little bit less experienced engineer. So what customer can do using our platform, customer can receive private tutoring, can receive mentoring on our platform. The customer can take online courses. The customer can read technical articles, blogs, and of course also participate into those online webinars that we have now. And once it's, let's say, in the move and a little bit in the progress, the customer starts gaining experience phase. So he will transition into industry typically, start working on the projects, on some industrial projects, on some products, developing some applications, and gaining experience by doing that. And once several years passed, the maturity began and the customer gained some experience, he can transition into the second user type, which we call partners. So the partner is basically a private individual or an entity that can give a private tutoring, give a consultancy, be a mentor to a customer. The partner can create and sell online courses, so be a content creator on our platform. And the partner can join also industry projects as a freelancer or a freelancing agency or independent, let's say, engineering office, and work on industry projects as an independent entity. And in that way, the circle closes, and we call it, that is why we call it a full cycle engineering. We call that concept as a full cycle, let's say. And why we do it? So our motivation or our mission is we are happy to be able to accelerate and optimize the diffusion of electrification worldwide. And by providing such a engineering platform, and by the way, we are providing also useful engineering tools such as project management tools, video conferencing tools, cloud sharing space, also tools to develop and create an online course and distribute it and sell it. So basically all of these instruments are inbuilt into the platform. And that is why we believe by providing such a platform, such a space, we contribute to enablement of the global cooperation and knowledge sharing. And now I would like to go to the actual webinar topic of today. and introduce you the speaker, Suleiman Nisanoglu. Suleiman is a mechanical engineer with 12 years of professional experience, both in academic and practical background in thermodynamics and CFD in computational fluid dynamics. He holds a master's degree and with his research focusing on CFD analysis for PCMs, for PCM integration in solar energy systems. He further deepened his experience throughout his doctoral research on thermodynamic cycles. And in that way, Suleiman is proficient and in advanced simulation tools, primarily utilizing ANSYS Fluent for his CFD analysis, but also beyond commercial software, he demonstrates a profound understanding of the numerical methods itself by developing and implementing his own finite volume codes in MATLAB for academic research. And his core areas of experience include numerical methods, differential equations, energy management, and hydrogen energy. So I'm happy to have you as a speaker, Suleiman, and you can now switch to your screen and start screen sharing and going through the slides.
Thank you so much, Dimitri. I will share my screen. Can you see my screen?
Yes, we can.
Super. Welcome, everyone, and thank you for taking time to join me today. In this session, we will deeply explore the highly efficient world of nanofluid and how we can model their thermal behavior computationally. Before we divide into governing equation, fluid dynamic, let me briefly outline the roadmap. We will start with fundamental question: what is a simulation? What is the simulation? To establish our computational mindset. Then we will scale down our perspective to understand what is a nanometer and why size matter so much in physics. Once we grasp the physical scale, we will discuss the core thermal mechanism, heat transfer with nanofluid. Then we will investigate why we use them instead of conventional coolants and how they work at a microscopic level. Finally, I will introduce our specific problem description, which will bridge the gap between theory and practice. This will lead us directly into our live and detailed ANSYS calculation demo. What is the simulation? Let's begin by defining what we actually do when we sit in front of computer to run simulation. Look at the real world deposit on the left side of this side of the slide. It consists of the continuous matter, almost infinite number of interaction particles, chaotic and complexity. As engineer, we know that Navier-Stokes equation cannot be solved analytically for much complex real-world geometry. We simply cannot write and solve equation for every single molecule flowing inside a pipe. Therefore, we rely on simulation. Simulation is the mathematical art of converting this continuous physics space into finite solvable matrices. In the computational world, we can call this critical process discretization or meshing. As you can see the flow chart, whether we use OpenFOAM or ANSYS Fluent, the logical workflow is identical. We define our physics boundaries in geometry. Then divide this domain into finite element during mesh phase. Next, we define our physics, fluid properties, and boundary condition in setup stage. We hand it over the iterational solver to crunch the number, and finally, we interpret the result. And in this way, we can analyze nanofluid. What is the nanometer? We are talking extensively about nanofluids, but what exactly is a nanometer? It's critical to properly visualize this incredibly small scale. On this slide, you can see logarithmic scale start from familiar object down to molecular level. For instance, a strand of human hair is roughly 16 micrometer thick. Red blood cell, 7 micrometer. If we zoom in with an electronic microscope, we pass biological viruses at 100 nanometer. Finally, we reach a single water molecule at about 0.1 nanometer. When we say nanoparticle or simulation, we generally mean engineered solid particle in the 10 to 100 nanometer range. 10 to 100 nanometer range, like virus scale. They are larger than water molecule, get small enough to remain suspended in the fluid without rapidly settling due to gravity. Here, why do we bother adding this extremely thin particle to a simple fluid? The answer lies in the limitation of conventional coolant like pure water or engine oil, which have poor thermal conductivity. Solid metal and metal oxide like alumina, however, are excellent thermal conductors. By homogeneously suspending these nano-sized particles in a liquid, fundamentally alter its thermophysical properties. If you look at the magnified illustration, you see base fluid or molecules surrounding the larger solid particles. Because this particle incredibly small, they undergo intense Brownian motion. This erratic zigzag movement, create microscopic convection currents within fluid itself. The particle continuously collide, transfer heat rapidly, and effectively disrupt the thermal boundary layer. This highly dynamic micro-level interaction is secret behind the massive enhanced heat transfer performance of nanofluid. That is very important, this Brownian motion. And here, we can have different way of to analyze nanofluid. How do we move this brilliant theory concept into computational environment like ANSYS Fluent? In CFD, we generally have two main numerical approach to tackle nanofluid. First method, actually best method, single phase modeling. Here, assume the solid nanoparticle and liquid are in perfect thermal hydrodynamic equilibrium. We treat the mixture not as two separate material, but as single entirely new fluid using specific empiric correlation. This empiric correlation based on experiments, and if our experimental result is correct, our single phase modeling must be correct. But the second way, more advanced approach, two-phase modeling, which is highly complex and demands more computational power. Single-phase modeling is easy and quick, but two-phase modeling hard, and demands more computational power. Under this, we can use Eulerian approximation, such as the mixture or the Eulerian model. Alternatively, we can use the Eulerian Lagrangian approximation, such as discrete phase model, to track millions of individual particles. For our live demo today, we will focus on particle Eulerian multiphase approach, Eulerian model, and mixture model. This is our problem description. Before the opening software, let's explicitly define the thermal problem we are going to solve. We will investigate forced convection heat transfer inside a standard straight circular tube. The tube has a total length 1 meter. Maybe I will select 0.1 meter length for calculation speed. And the internal diameter is 0.01 meter. The working fluid is a nanofluid containing perfectly spherical 100 nanometer metallic particle. Maybe I can select a 40 nanometer for thermal properties of the article. I will apply an article. I rely on this article. The volume fraction, the nanoparticle inside base water, is set 1%. The fluid enters the tube with a uniform temperature 293 Kelvin. As it flows, it is subject to constant wall heat flux, 5,000 watt per square meter along the outer surface. Our engineering goal is observe the internal temperature distribution and evaluate enhanced heat transfer coefficient. All right, we will establish the theory and define our boundary condition. It's time to get our hands dirty with the actual CFD software. Maybe you can open your ANSYS workbench and follow my steps closely. I will close my PowerPoint presentation. First of all, I touch the fluid flow Fluent here, and I use design modeler. I am old school guy. Right click on geometry, and I select design modeler. That is old ANSYS geometry. Space claim is new one, and the Discover is the newest one, but I use this one. You must wait. Our radius is 0.01 meter. Okay. I hope my geometry is open. Starting design modeler. Yes. First of all, I select plane and right click, look at. Then I click new sketch and click sketching. I use rectangle. Why? We create circle pipe, but I click rectangle because of I want to draw half of the pipe. And I will select axial symmetry for the calculation. Yes. And I click dimension, click vertical. Vertical length is our radius, 0.001 1 is our diameter, 0.5 radius. Then we can click horizontal length. 1 meter is very long. Maybe we can select 0.2 meter. Enough, I think. After that, I click this concept menu here, surface from sketch, and select sketch 1, click apply, then generate. So click concept, surface from sketch, and select sketch, then generate. And we can close this window. In meshing, this is important for two-dimensional case. For two-dimensional case, I use ANSYS meshing, but the three-dimensional case, I use Fluent meshing. Actually, three-dimensional case, we can select this one, Fluent with Fluent meshing. Fluent meshing better than this meshing for three-dimensional case. In meshing, we apply edge sizing with a bias factor to concrete the grid near the wall where thermal gradient are steeps. Here, first of all, we select insert sizing, and here edge. Click on keyboard CTRL and select not here. This one, pardon, select here and here. Inlet and outlet. On geometry. And type is number of division. I select 10 part. Okay, maybe 5 part first of all. I want to see bias because of maybe we must reverse bias here. Then bias type, this one, and bias factor is 4, for example. Very nice. This side is good. Maybe in other side. Yes, in other side is reverse. We select reverse bias here, left bottom, here reverse bias, and select this edge, click apply. Okay, now bias is okay. Then in other insert sizing, select up and down horizontal edge, number of division 200 without bias. Very nice. Then right click face meshing, click this face, and I want to change something. For example, edge sizing 20, number of division is 20, and blend to neighbor must be no. This is new one, but I don't use. Also this one, and click generate. Classic two-dimensional rectangle mesh here. And we can select edge and left vertical edge. We give inlet, create named selection, inlet. Bottom horizontal line is axis. And here upside is wall. and right side is outlet. Very nice. Yes. Now we can launch the Fluent. Close this. Of course, we must right click to update. First of all, we must update. First of all, I want to make analysis with single phase model. Here, this article is Q2 journal article 2021. And we can investigate this. First of all, this table 1 is properties of aluminum oxide and copper oxide. Very nice, we will use this. Also, we can use these thermophysical properties for single phase modeling. For example, 1% alumina here. That is very easy, but the most correct way in nanofluid calculation is making experiment. After that, the experimental result like this, use single phase model. First of all, I can click Fluent, ANSYS Fluent, and we launch in double precision. We set the for here, double precision, and we can set solver processor, for example, 4, which you have. Click Start. Anyway, we can focus on the article. For example, here is 1% alumina and water nanoparticles, and 2% and 4%. Very nice. Here, this one is hybrid model. Very good article. And of course, after this course, you can create yourself this single phase modeling, and you can analyze with, of course, good literature review. You can also get good resource. Okay, first of all, we set the solver pressure based. Then I use axial symmetry for the increased calculation speed. Axial symmetry. Then model. Multiphase is off. First step is single phase model. Then energy equation is open. And material. Of course, I will work on this case. Must be easy and of course quick. And I select laminar flow. I decrease the velocity. Then we can click material and create edit and single phase modeling. Maybe alumina with water. 0.0 alumina 1%, yeah? Not, yes, 1%. 0.01. Okay. And we can enter this density here, 1023.129, okay. And CP value 4058. Thermal conductivity and viscosity. Pascal times second. Dynamic viscosity, nice. 9, 10 power minus 4, okay. Yes. Like water, we can use this fluid in our analysis. After that, boundary condition, we can give inlet value. 0.01 meter over second and 293 Kelvin. Okay. And wall, we give heat flux 5,000, isn't it? Yes, 5,000 watts over meter square. Okay. Axis is axis and outlet is pressure outlet. Very good. After that, we can select coupled schema. Pressure is second order, momentum is second order, very nice. Pseudo time method, okay. And click hybrid initialism. Initialize it. And we can solve. Normally, iteration number must be 1000, but our case is very simple. Maximum 16, 19 60 and 90 iteration is enough for us. And we can start to calculate. Very nice. With single phase model, yes. With single phase model, we have no calculation time. Or look like water analysis, very easy. 69 iteration is enough, this one. Maybe we can see contour, well, temperature contour, total temperature here. Okay. Maybe we open Word. Here, this one is single phase. Maybe firstly we must have base fluid, water only. Create material, fluent database, fluid, material type is fluid, and water liquid. Okay. And cell zone condition, we can change material. Click edit. Alumina, no, water. Okay. We must initialize again because of delayed alt result, and run again. Here, maximum temperature single phase model 318. The border here, this one is 319. This meaning single phase model, the energy dispersed inside the water body, not only edge boundary, not only boundary, dispersed the all body. 1 minute, hop. Here, yes. We can now here base fluid, pure water. Now we can analyze the system. Maximum temperature at the boundary, outlet boundary, 319, and here 318. We can see the energy dispersed to water body. And can you see here the green area is near the bottom here, but here blue area is big. The base fluid has blue area. The cold water is very little big. Of course, this is 1%. Then we can start multi-phase model setup. Here, our material now, base fluid, water liquid. Okay. Here, multi-phase. I click model. Well, sorry. I click model, multi-phase. And first of all, I want to click mixture model. Model parameter is slip velocity, and equilibrium phase is 2. One of them is water, another is alumina, for example. Of course, first of all, we need the material. Click materials, create edit, and Fluent database, and material type must be fluid. And material type must be fluid, but we select aluminum solid. That's very interesting, yes. Aluminum solid here, and click copy. Okay, and I will change this aluminum solid as alumina. Aluminum 2O3. Alumina. And the thermal properties of the alumina in here, table 1. 360 density, 4000 or 5 here. 765 specific heat capacity, and thermal conductivity 36. Viscosity not important in this case. And close and select multi-phase flow. Yes, here. I select mixture model and slip velocity, click apply. Then phase 1 is our water, phase 2 is our aluminum oxide. Phase 1 is water, phase 2 is aluminum oxide. Very nice. If using eulerium, we must check granular option for phase 2. Granular, that is very important part. And the particle diameter is here, and our case particle diameter is 45 nanometer. In article 45 nanometer, okay. 45 10 power minus 6 meter, pardon, here, diameter is here, 45 10 power minus 6 nanometer, yes. Now, under the fuzz interaction, after that, we click fuzz interaction. The fuzz interaction menu, we have the define how the fluid and solid particle physically influence each other. Looking to force type here, especially drag coefficient, we open the drop-down menu, select Schiller-Neumann. The specific empirical correlation is excellent and widely accepted for modeling solid spherical particles suspended a primary liquid. Next, we switch to the interfacial area. Here, AI symmetric or AI particle. We can select AI symmetric, IA symmetric, or IA particle. That both of them good for us. We can use both of them. The critical settings define the contact area density between the water and nanoparticle, which directly dictate the interface heat transfer rate. And finally, we check the population balance model tab and make sure the method is set to off. We don't need this model because of nanoparticles are rigid solid. They do not cause to form larger drops like bubbles, nor do they break apart. We use this population balance model for like bubbles. And click apply. And here, the boundary condition, and we have two inlet here in the right side, two inlet. Inlet, first of all, we click inlet and thermal. Yes, thermal temperature value, okay. But we can click this plus button, left side the inlet, and we can give velocity number and volume fraction for each phase. For phase 1, water 0.01, okay. For phase 2, must be same, of course. Yes, 0.01. Also, we can click multi-phase, and volume fraction must be given here. Volume fraction is very important. I give 1%. And click apply. And we finish the analysis for multi-phase mixture model and click hybrid initialism. Wow, very quick. Okay, very nice. And click run. Iteration number must be little increase, maybe 70, 80. We will see. because of our new, oh, very nice, very good. Here, now our temperature of the boundary is decrease, more decrease, 314 here. For mixture model, maybe we can see both of them, mixture model and single phase model. Here you can see now, in single phase model here, in single phase model, you can see blue area is bigger than mixture model. The green area in mixture model is bigger here. And maximum temperature in single phase, in base fluid, maximum temperature 319. Sorry for this. What is this? Sponsored. Very nice. Okay, yes. 319 and here 314 for total temperature. And lastly, I will quickly analyze Eulerian model. Click multi-phase model, same, everything is same. We can click Eulerian inhomogeneous model. Both fluid particle, this meaning both fluid particle is inhomogeneous mixture. Of course, we can use this menu for boiling and condensation. Anyway, apply this. Also, phase is same, granular. The granular is most important thing actually. Primary phase, and everything is same. Only maybe we can change this correlation. For example, I prefer Ransmarshall correlation for Eulerian, but also you can give your user-defined expression, your selected correlation in this here, this article, this style article, with good literature research. This is very good gun for the create good journals, good articles. It's very good. Anyway, we can continue, and it must, of course, must be initialize and click run. Normally, this two-phase model longer than single-phase model, but this time, last time, the mixture model is very quick. I wonder here 1, 2, 3, 4. Wow. Yes. Very nice. Mixture model and Eulerian model, the maximum temperature value is same. Can you see? 341. I don't want to copy this. Okay. Until here, could you have any question? Now I want to finish my screen sharing. Thank you for listening.
Thanks a lot, Suleiman.
My pleasure.
Just checking the chat now. So, ladies and gentlemen, it's the best time to ask some question to Suleiman, since we have him online. So please write it in the chat, or you can raise a hand, or you can speak and ask something regarding the webinar, the material. Let's check in the chat. Yeah, I think I have received one question. Just let me check it. Yeah. So can you see it, Suleiman, in the chat?
Now, yes. In the real life, in experiments, we can buy nanofluid, nanoparticle, and of course we need a laboratory, and we can very good calculation measure. Of course, we need some measurements like mass and I don't know, distillation machine. For example, we have distillate water. After that, mixed, manually mixed with nanoparticle, and nanoparticle is buying on internet. You can buy nanoparticle. For example, gold and silver nanoparticle is very popular this last year. Until last year, gold and silver nanoparticle is very popular.
Is it answering your question, Vita? Or if you have a follow-up question?
Of course, we use in real life this nanoparticle, for example, cooling motors, electric motors with oil cooling motors in critical process, of course. Not only our cases is household things, but in critical electrical motor cooling, electronic cooling, we use nanoparticle. My pleasure.
Yeah, I have posted another question in the chat, so I have received that.
K criteria. Actually, the K criteria is study on the articles. For example, good experimental result, single phase model is best and easy. But we must check the result, the validation, experimental result validations. And also we can use our user-defined correlation for the multi-phase models. You can improve, of course, our model performance, but in basic case, I think a mixture model is less problematic multi-phase model. But if I have a lot information about the material, I select single phase. For example, in my case, I sent a journal. I sent an article to journal. First of all, for alumina, I use single phase model because of I had lot information. But gold nanoparticle, I have not good information, and I must use mixture model.
Right. Yeah. Makes sense. And we have received another one. I also pasted that in the chat regarding the application in future or current applications.
Actually, electronic cooling and solar battery cooling is very important, the potential of the nanoparticle, because of big size. For example, data center cooling is very important for countries, of course, because of data center is not only Google and Facebook, but also in army and critical bank system is in the data center. And then countries that data center cooling is very popular and very important. And in potential, I think data center cooling will be important.
Right. Yeah. Thanks a lot. So any more questions from attendees? It's the best time to ask something. since we have a live webinar now and we have Suleiman on the line. So I will just in the meanwhile switch back to the presentation. Yeah, let's then, if we don't have any more questions, let's wrap it up real quick. So I just wanted to show you also the remaining opportunities beside the webinars, what we have on the platform. You as a webinar attendee, you will receive a discount code WiredWide10, which will allow you to get 10% off for purchasing any online course on our platform or a private tutoring regarding CFD analysis, regarding the nanofluids topic or ANSYS Fluent. We have tutors on the platform that are ready to support you, ready to help you. We have, of course, Suleiman. If you have some questions after the webinar, you can always reach out to him on the platform. He is our member, obviously. And we have also some useful online engineering courses as well, so you can check them out. You can also filter out the CFD related topics or CFD related courses and check them in particular, that it will help you in your career or in gaining some more experience in that field. So the links are below. Yeah, and don't forget to use the discount code WiredWide10. So I think that would be it for today. Any final words from your side, Suleiman? You are muted. You are muted, Suleiman.
Sorry, repeat again, please.
I was wrapping this up and I was asking whether you have any final words to attendees from your side.
No, thank you so much.
Yeah,
Thank you for listening.
Yeah, it was very great, insightful webinar with live demo in ANSYS Fluent. So I enjoyed that a lot. Thank you so much. Also from my side,
pleasure.
It's always high quality webinars with you, Suleiman. I enjoyed that one as well.
Thank you
That's
so
not
much.
the
My
first
pleasure.
one. Yeah, and I think and I hope this is not the last one. So yeah, thank you so much, Suleiman. Thank you so much, dear attendees, for tuning in. And yeah, I hope you enjoyed that as well. We will distribute the slides after the webinar. We also send the PowerPoint presentation to all the registered attendees. And you can also claim a certificate. If you need one, you can write us a message and claim a certificate for the webinar attendee. So all the infos will be once again placed in an email and send it to you via email shortly after the webinar.
Of course.
So yeah, thanks a lot, everyone, and I hope to see you again in the next one, and looking forward to the next one, and have a great evening. Thank you so much.
Thank you.
Bye-bye.